I have a model here that tests data from school districts in a state in the United States. The model has 4 variables: years of experience on average by teachers in each district, in-school suspensions, the number of in-school suspensions in the district, and the number of out-of-school suspensions in the district, and SAT scores in the district. And I'm testing a model here in which I'm hypothesizing that years of experience affects in-school suspension. Years of experience also affects out-of-school suspensions, affects SAT scores as well, and in-school suspensions and out-school suspensions affect SAT scores. So the results here suggest that years of teaching experience by the teachers tends to have a negative. This is a nonlinear analysis that was conducted. So the model refers to a nonlinear analysis. I'm sorry, it refers to a linear analysis. Let me just double check. I can see that by viewing the general results, and yes, the algorithm using the analysis PLS regression. So this is a linear analysis. So what seems to be happening here, according to the model, is that years of experience by the teachers tends to lead to a reduction in school suspensions. More years of experience by the teachers tends to lead to reduction in out-of-school suspensions. Now, neither of these variables significantly affects SAT scores, and I can see that the p-values indicate that. And what I should look for here are potential problems in the model. One of them would be collinearity, which I can check by going to the View Latent Variable Coefficients window. And I would expect numbers ideally lower than 5 here, and no greater than 10. So they're lower than 5, so that doesn't seem to be a problem. I don't have any negative R squared or Q squared coefficients, but I need to check to see if there are instances of Simpson's paradox here, where I would have path coefficients with a sign and then correlation coefficients with a different sign. And I'm going to do that by opening the table with correlations among latent variables, and also this table with the path coefficients side by side. So when I compare these path coefficients that I see here with the correlation coefficients, I see that in one case, only one case, which is this case here, this path coefficient is positive and the correlation coefficient is negative. So what this tells me is that perhaps this variable doesn't belong here. So this link, mediating link, doesn't belong here. So what I'll do is I will redo the analysis with a different model, excluding this variable from it, and see what the results are. Okay, so here is my new model, now without any instance of Simpson's paradox. And then I have that years of experience tends to reduce in-school suspensions, interestingly. So the more experienced the teachers are, the fewer in-school suspensions end up happening. This may be due to the fact that more experienced teachers can manage students better in order to avoid in-school suspensions. And years of teaching experience also seems to have a direct effect on SAT scores when we control for the effect of in-school suspensions on SAT scores. Now, here's the interesting thing that I wanted to emphasize in this analysis, is that I have a direct effect of years of experience on SAT scores, but the total effect should also include this path. And when I look at the total effect, I'm sorry, got to go to this one, View Indirect and Total Effects. Now, resize this window so that I can see it side by side with this graph with the direct effects. So when I look at the total effect here, the total effect of that years of experience has on SAT scores, I see that it's actually higher than the path coefficient. Why is it higher? Because it considers this other indirect effect as well. So my conclusion here is that for each year, each standard deviation variation in years of teaching experience, I have a 0.235 standard deviation variation in SAT scores. I can actually come up with the actual numbers here that I could use to report these results to someone who is not as well versed in statistics by doing some simple calculations. So I'll open an Excel spreadsheet where I'm going to be doing these simple calculations. So first of all, let me get this number here. So this is the path coefficient. So the beta coefficient is 0.235, and I'm going to get now for years of teacher experience as SAT scores, I'm going to get the means and standard deviations. So I'm going to go to data and to this first table here, and here I have for average years of teacher experience, I have the mean and standard deviation. So I'm going to copy these values into the spreadsheet. I'll paste them here. So this is the mean, this is standard deviation, and this is for years of experience. And for SAT scores, I also have the mean and standard deviation here, which I'm going to copy into the spreadsheet. So I have mean and standard deviation. And this is for SAT scores. So I can say that for each 1.64 years, additional years of teacher experience, I have a increase in SAT scores of 17.92 points. So that's, and I can play with this number to give different results. For example, for each unit of standard deviation variation, for each additional year of teacher experience, I would have, if I divide this number by this, I would have an increase in SAT scores of 10.91 points. So I can actually tell my client organization here that is interested in this study exactly what those standardized numbers mean by doing these simple calculations on a spreadsheet.